I'm Shravan Hariharan.
I'm Kevin Hom.
I'm Michelle Kent.
And I'm Shivani Shah. Our project is the Nanotechnology of Foam with a focus on water filtration.
Today we're going to start by telling you a little bit about our motivations behind our project, which is the depletion of clean water. And then we're going to move into a little bit of chemistry of what the sol-gel process is. We're going to talk a little bit about the filters that we tested, go into our experiments, results, analysis, conclusions, and future directions.
So, clean water is a necessity for human life, yet it is one of the scarcest quantities in developing countries. Over 750 million people don't have access to clean water every day, and those who do often have to pay a high price for it. Commercial water filters are effective in decontaminating water, but they can't trap the smallest viruses and bacteria, and they are often way too costly for developing countries. A solution to this may be the sol-gel process. This process creates foams and gels that are solid and porous, who have pores ranging in size from 2 to 10 nanometers. This is large enough to allow water to pass through, while in theory trapping any contaminants, including viruses and bacteria, the smallest of which range to about 40 nanometers in size.
As Shravan said, the sol-gel process is a method used to create porous gels and foams. This involves taking a chemical precursor such as silica, alumina, or zirconia and adding it to a liquid medium such as water. If the solution is left to sit, then the precursor molecules interact with each other and with the water molecules through van der Waals interactions to form a self-supported network. This is called a gel. If you evaporate the water from the gel, then you get a foam. Now, the foams that we make can be manipulated in many different ways, depending on which chemical precursor you use or which catalyst you use. For example, silica aerogels, which are a very common type of aerogel, are made by using colloidal silica or tetraorthosilicate, also known as TEOS. The aerogels that result from TEOS precursors are hydrophilic. However, if you replace TEOS with methyl-triethoxysilane, MTES, then you get a superhydrophobic aerogel. The reason for this is because if you look at the TEOS molecule in figure 7, you can see that there are 4 oxygen atoms. But in figure 6, the MTES molecule, there's only 3. This is because, or the reason why the TEOS aerogel is hydrophilic is because it has 4 very electronegative oxygen atoms within the self-supported network, but MTES only has 3, and so that adds to the hydrophobicity of the aerogel.
So for our experiment, we aim to make water filtration units that are cheap, efficient, and large scale. We did this by analyzing different materials and ascertaining their filtration properties. So the first thing we did was we tested common filtration components, such as charcoal, gravel, or sand, and then we ran contaminants through them to get their properties. Next, we also did tested sol-gel products, and compared their properties to the properties of common filtering components. And then we created mixed media filters, which are filters that have different components within it. And we use those mixed media filters to figure out the best combination and organization of the different filtering components within it.
To approach our experiments, what we did was we took an aerogel and we placed it inside a beaker and we put a burette directly on top of it and we poured water through it. So the idea was to have the water go through the pores of the aerogel, since aerogels are very porous, and in doing so leave behind particulates and other contaminants inside the foam. So we also did a similar procedure with the gels.
So, as Michelle mentioned earlier, a lot of our experiments involved mixed media filters. Now, these filters consist of different filter beds, layers, each with a different material. Our materials were always a coffee filter at the bottom of the filter, and then we had charcoal, coarse sand, fine sand, gravel, and ceramic beads. Now, we tested these filters from both coarse to fine, with the gravel at the top and charcoal at the bottom, and from fine to coarse, with the charcoal at the top and the gravel at the bottom, because we wanted to see how the order and size of filtering materials would affect the rate of filtration and the quality of filtration. We also created one filter setup without the charcoal, because we wanted to see if the charcoal would actually help the filtration or contaminate the water further.
After we made the filters, we made a contaminant solution to test how effective the filters were. So the contaminants we used were starch, sugar, protein, food dye, and vegetable oil. We also used various indicators to put into the filtrate, the stuff that came out of the filter, in order to detect the presence of the contaminants. So for starch and sugar, we used indicators such as Lugol's or Benedict solution, and for protein, food dye, and vegetable oil, it was relatively easy to visibly detect whether the contaminants were present in the filtrate. For protein, we looked at how opaque the filtrate was. For food dye, we looked at the color because we used a bright red food dye, so it was easy to tell if there was contaminant in the filtrate. And for vegetable oil, we looked for a layer of oil on top of the filtrate solution.
So in addition to the contaminants that Shivani just mentioned, we also had liquid contaminants that we use for the mixed media filters. We ran tea and a Coca-Cola/Pepsi solution through the filters to see so that we could analyze differences in color and pH. Now we also looked at pH because we realized that that we want the filtrate to be neutral, relatively neutral, which is neither acidic or basic.
Our general results for all of our experiments were that water did not pass through either the gel or the aerogel. Also, starch, sugar, oil, food dye, and tea were all present in the mixed media filters that we tested, which means that they, at this point, cannot compete with commercial popular water filters. In addition, when we were observing the activity of the contaminant solution flowing through the mixed media filters, we noticed that in general, as the pore size of the individual filtering component decreased, the flow rate also decreased. This was a general trend, except for the case of ceramic beads. Now, the reason for this, we believe, is because although ceramic beads in small or in large amounts have very large pore sizes compared to fine sand, ceramic beads also have a surface chemistry that interacts with water molecules through adhesive forces, and so attracts water molecules and doesn't let them fall through the filter very fast. We speculate that since the surface chemistry of the ceramic beads can affect how the water molecules flow through the mixed media filters, then future chemical modifications to our hydrophobic aerogels could attract water molecules more and allow water to flow much more substantially through aerogel filters.
So what ended up happening with our sol gel product testing is that we placed a whole liter of water concentrated through the burette directly on top of the aerogel, and despite being having so much force, no water went through because the foam was so hydrophobic, super hydrophobic in fact. And for gels, we originally thought that 10 milliliters passed through one layer of gel in about 10 minutes, but we later discovered that when we poured tea through this gel, the macromolecules in it weren't filtered through, so we realized there was a crack. And for two layers of gel, it took a whole 5 days for 2 milliliters to pass through. So we found that they weren't effective filters.
So regarding our mixed media filters, we found different pros and cons to both fine to coarse and coarse to fine filters. Fine to coarse filters work better than coarse to fine filters in the respect that fine to coarse filters are able to get out more contaminants. However, the fine to coarse filters also take a lot more time to filter out materials than the coarse to fine filters. In addition, when we ran water with food dye through both of those filters, we noticed that the coarse to fine filters were able to take out most of the food dye, while the fine to coarse filters didn't work really at all. We also used alum to see how it would affect the filtrate. Now, the alum is supposed to be a flocculant, which means it draws together the ions within the water, and we noticed that it was able to get rid of most of the coloring in the filtrate. And in regards to the experiment where we took away the charcoal from the filtration unit, we noticed that with the removal of charcoal, the filtrate turned a darker color, so we believe that charcoal actually helps with tar filtration.
So as Michelle just mentioned, the charcoal actually improves filtration, it doesn't hurt it. And the reason behind this is charcoal's dual pore nature. Now the grains of charcoal themselves have very small pores, from 1 to 3 nanometers in size, and then there are also pores between the grains themselves. So this exposes the contaminated water to a larger surface area of the filtering material, so it's filtered more effectively. In addition, when we used alum, it is effective in removing ions. It is a coagulant, so it groups all of the ions together, which were the fine particles in the tea, and the groups are large enough so that a single coffee filter can remove them, so this greatly increased the quality of our filtrate. And finally, we tried using titanium dioxide and PEG, polyethylene glycol, to make a solution that would turn our foam from hydrophobic to hydrophilic, but our foam actually repelled this solution, and our foam retained its hydrophobic nature, so without the addition of any other chemicals, this solution is ineffective in changing the hydrophobic nature of the foam.
Now, in addition to the results we gathered from our experiment, we also performed a cost analysis. This is mainly because one component that we're looking for in our filters is that they are relatively cheap. Now, as you can tell that from the graph, that our filters that we created are a lot more cheaper than the filters currently on the market today. However, when comparing our filters to the filters on the market, our filters are a lot less effective at removing large quantities of water contaminants from the water. However, we hope that in the future, if we had more resources and time, we'd be able to expand upon the filters we created and improve them. But we don't believe that it will go above the prices of those currently in the market.
We learned quite a few things in the lab from our experiences. One of the things we learned is that without modifying the surface chemistry of our foams and gels, they're currently not effective filters because of the super hydrophobic nature of them, which repelled water. We also learned that by taking advantage of the mixed media patterns that we investigated, we can use these two as opposed to individual filtering components to create more effective filters. And one thing we want to do in the future is we want to coat the aerogels each end with an enhanced titanium dioxide solution to make them hydrophilic. And in doing this, we can possibly mimic a cell membrane by sandwiching, two hydrophilic layers surrounding a hydrophobic center, so that when water gets attracted to the end, it'll go inside the center of an aerogel and be repelled out to filter water more efficiently. We'd also like to try changing the pH of the coating used, because typically polluted water is acidic from acid rain and heavy metals and such. So if we change the pH of the coating to be more basic, we could potentially neutralize polluted water or liquids that we filter through. And we'd also like to try just starting by using hydrophilic aerogels, despite them taking much longer to synthesize.
So another important thing is to determine the optimal placement of our sol gel products within current filters. Now, because the sol gel products have different properties than the rest of the filters, important research needs to be done to see where they are the most effective in decontaminating water. For example, if you place a gel at the top of a filter, it would very slowly filter out the contaminated water effectively, but then the gel, if it's flaky like ours were in the lab, it could contaminate the rest of the water again, and that would be a problem. But if you kept the gel at the bottom of the water filter, it could be contaminated by the other filtering materials, which is something that needs to be tested. And most importantly, we need to develop a quick, cheap, and large-scale filtration unit. Now, the filters we were currently using were both small and fragile, so they weren't cost-efficient or time-efficient because they took very long to filter the materials. So if we determine a quick and cheap way to make this on a community scale, it can be used to replace the costly alternatives that are actually being used in developing countries today.
We'd like to thank our mentor, Dr. Lisa Klein, for allowing us to use her lab and allowing us to have an amazing opportunity to experience real-world research.
And we'd like to thank our project mentor and RTA Elizabeth McGinley for guiding us through this project and overseeing us in the lab every day.
Furthermore, we'd like to thank the director of the Governor's School of Engineering and Technology, Dr. Eileen Rosen, for helping to make this possible.
We'd like to thank the Associate Director of the Governor's School of Engineering and Technology, Dean John Patrick Antoine, for providing us an exceptional management of the Governor's School program.
And we'd like to thank the New Jersey Governor's School of Engineering and Technology overall for allowing all of us the opportunity to learn more about STEM in the real world.
And we'd like to thank Rutgers and all of our sponsors and the state of New Jersey for continuing to fund this program and keeping it at the level of excellence it has been maintained at for the past many years. Here are our references.
Thanks so much for listening. If you have any questions, please ask them now. Yes.
You said you weren't able to use your gels as water filters. Would you consider that a failure?
We actually would consider it the opposite of a failure. It is a success. Even though our gels weren't able to be used as viable filters in the resources and time we were given, this gives us important information for future research that tells us what doesn't work, so we can focus on what will work instead. And we also learned a lot about the properties of sol gels and of water filtration in general, which can be applied to future research to develop in the future a sol gel filter or just a mixed media filter that can be used to effectively filter water in a cheap scale.
Yes.
Yeah, so you were mentioning the foam is hydrophobic. So have you kind of treated with alcohol just to make sure that actually, the pore size you're saying is a couple of microns? So at least if you put it with a alcohol, would it flow through? Or if that's the case, if you put alcohol in it, it could have reduce the surface tension on the pore size, and then after that, then we kind of like treating it, the filter as you were suggesting using a PEG and other hydrophilic molecules. So you can rinse that with alcohol, and if it does come through, maybe after that, the water can actually come through after that. You reduce the surface tension.
Yeah, we looked into adding alcohol to our aerogels. Actually, the titanium dioxide and PEG solution that we had also often has alcohols in it to help allow or to make the surface of the aerogel more hydrophilic. However, alcohols are harmful to human beings, I guess. If we were to filter water through the aerogels with the alcohol coating, then it might recontaminate the water as it passed through, and so it wouldn't be healthy for human consumption.
But that's just the concept that actually the pore size, given the small size of the pore size, like you can actually get something through the pore size. So a lot of times the foam could be pre-treated with alcohol, and then you filter it through after the first liter of it, and the next liter of water could be useful.
Oh, so you're saying put the alcohol in first and then...
It's like a rinse first, and then allow the aqueous comes through.
Oh, yeah. That's definitely a future direction that we can take.
Those are some of the things we planned in our future directions, but we didn't have the time or resources in this lab to completely pre-treat the foam, and we wanted to focus on things we were dealing with currently. Yes? Third.
Yeah, what's super hydrophobicity?
So, hydrophobicity is how well a substance attracts or repels water. And superhydrophobicity is defined as contact angle being greater than 150 degrees. So contact angle is a measurement of hydrophobicity, and how it's basically measured is typically using a goniometer. Basically you have a surface, and let's say you have a water droplet. So you place the droplet on top of the surface, and if it's hydrophobic, it'll bead up. Otherwise, it'll sort of like collapse, I guess. And you take what you do is you take the line tangent to the water droplet at the interface, and if it's the smaller it is, the more hydrophilic it is. The greater it is, the more hydrophobic it is. And 150 or greater is considered super hydrophobic.
Last question.
Sure.
How did you guys split up your roles in this lab? Who had responsibilities and activities?
Well, it was kind of dependent on the lab itself, like what we were doing. Usually, Shivani and Kevin were working on trying to do the test for the contaminants, though we all did that at some point. Well, me and Shivani usually made the filters, but we all did the filtering at some point. I usually wrote in the lab notebook the results, and we all really looked at made sure that the experiments were happening at the same time.